In this lecture, we'll look at the first law of thermodynamics. The first law of thermodynamics is essentially the statement of the principle of the conservation of energy for thermodynamical systems. That is, the variation in energy of a closed system during any process is equal to the amount of energy that the system receives from the surroundings. In this lecture, we look at the formulation of the first law of thermodynamics for a closed system, and thereafter in future lectures we'll extend it to open systems. Now, we have seen earlier that energy transferred to a system can be in form of work and heat. However, this equivalence between work and heat was not as obvious historically as it appears to us now. Therefore, before we discuss the first law in more detail, it would be meaningful to look at a historical perspective of heat and work. So, originally, back in 18th century, heat was thought to be an elastic, weightless, and indestructible fluid called caloric. And this was back in the 18th century. And this fluid, caloric, was thought to pass through a body at higher temperature to a body at a lower temperature when brought in contact. And the increase in temperature of the body was thought to be due to an increase in the content of caloric in body. Now, in 1798, Benjamin Thomson, who was also known as Count Rumford, published a paper on his experimental work on heating of water due to friction. In his experiments, Count Rumford immersed a cannon barrel in water, and against that barrel he pressed a blunt cutter to the internal surface of the barrel that was rotating about its axis. And what he discovered was that one could heat water and boil water due to friction between the barrel and the cutter. And moreover, he observed that heat was liberated as long as the barrel was rotated. Therefore, Rumford concluded that heat is not a material substance such as a caloric, and an insulated body can liberate unlimited amount of heat due to friction. So essentially, the experiment of Count Rumford disproved the concept of heat as a weightless fluid called caloric. Moreover, this experiment showed that the amount of heat evolved during boring was proportional to the work done, and this inspired the work of Joule in 1840s. So what Joule did was he did experiments to establish a relation between the amount of work done to generate heat and the heat generated. That means Joule did experiments to find the equivalence between heat and work. Because now it might be clear that heat and work are forms of energy in transit, but back then it was not known. So the aim of Joule was to show that work and heat are equivalent and they're both forms of energy, and in particular energy in transit. So what Joule did was he constructed an experimental setup which had a vessel with insulated walls. This vessel was filled with water. and a paddle wheel was submerged in water. So this is a paddle wheel to stir water, and this paddle wheel was operated by a falling weight. So as the weight lowered down, this paddle wheel would rotate. And what it did was that you started with some initial state, and then the weight lowered down, and due to the change in potential energy, that is, if the weight went down by a height h, one could tell what is the amount of work that has been done on water. So one can quantify the work done on water by the change in potential energy. And then Joule measured the change in temperature of water using a thermometer. So essentially, for a given change in the height of the weight, Joule would measure the temperature of the water, that is the change in temperature of the water. And based on these experiments, Joule discovered that the amount of work done to raise the temperature of water was always proportional to the amount of heat that is required to bring about the same change in temperature of water. That means you could get that state of water. That means if you start from, let's say, with lower temperature and you go to a higher value of temperature, you could achieve that state of water also by heating rather than doing work. So the amount of heat that is added and the amount of work that you do to get that same particular state, what Joule found was they were proportional to each other. That means the work done to raise the temperature of water by a particular amount was proportional to the heat that is required to have the same change in state of water. In other words, work is proportional to heat. And therefore, what Joule found was that work is equal to J times Q, where J is the proportionality constant called the mechanical equivalent of heat. If heat is measured in calories, and recall that 1 calorie is the heat required to raise temperature of 1 gram of water by 1 degree Celsius, then if heat is measured in calories, then this value of J is equal to 4.18 joule per calorie. And in SI units, however, this value of J is equal to 1 because the units of work and heat are taken to be the same. And in addition, what Joule found that no matter how you do work on this system, for example, you could lower the weight, and then with that weight you could, let's say, run a dynamo that converts this mechanical work into electrical energy, and that, let's say, you use to heat up this water using a resistor or an immersion heater. Then what Joule found was that no matter how you do this work, the amount of work that you need to achieve the same temperature of water remains the same. That means this mechanical equivalent of heat was the same regardless of the way in which you do work on the system. You could do work by moving this paddle wheel. You could do work by converting this potential energy into electrical energy, which would heat up the water using a resistive heater. So what these experiments illustrated was a very important and a general principle, and that principle is If a thermally insulated system is brought from one equilibrium state to another, the work required to achieve this change is independent of the process used. That means you could heat up the water, let's say from one temperature to another temperature, that is from one equilibrium state to another equilibrium state, either by moving this paddle wheel or stirring water, or you could do mechanical work and you could convert that into electrical energy and heat up this water through a resistive heater, or you could do any type of work through any process. But if you have this closed system that is thermally insulated, that means it has adiabatic walls, then the work required to achieve this change, that is from one state to the other, is independent of the process that is used. To elaborate this statement more, consider that we have this system which has adiabatic walls, and this system is initially in state 1. Then you do work on the system and you attain a new equilibrium state which we call as state 2. And let's call this work with a subscript AD to denote that this work is done on the system having adiabatic walls or in a adiabatic process. So the Joule's experiment is exactly the example of such kind of a system where you have these insulated walls and you do work on the system. So what this statement says that no matter in what way you do this work on this system, you will attain the same state. So this statement says that the work that is required to transform this system from state 1 to state 2 is independent of the process, and that suggests that there must be a state property or a point function which we'll call u, for which we have u2 minus u1 is equal to WAD, that is work done on this system having adiabatic walls. And this is because we've seen that the work required to take this system from state 1 to state 2 is independent of the process that is used. That means this adiabatic work must be equal to the difference in some property of the system, and that property of the system we denote by U, and in particular we'll call this property of the system as internal energy. So this particular equation, which I'll call equation 1, is our first part of the first law of thermodynamics, and it's also called the restricted form of the first law of thermodynamics. If we consider a system such as that shown over here that does not have these heat insulated walls, that means it does not have these adiabatic walls, then clearly this statement is not going to apply, because this statement over here applies only for a thermally insulated system, and that's what experiments of Joule suggested. But if your system is not thermally insulated, then this equation 1 is not going to hold. That means we cannot write this delta U, that is delta U is equal to U2 minus U1, cannot be written or cannot be equal to the work that is done on the system to take the system from state 1 to state 2. And an example of such a process is an extreme example. In fact, if you look at this system of Joule, then you can go from state 1 to state 2 without doing any work, and you can do it if you don't have these insulated walls, then you can do it by supplying heat to this system. Therefore, if the system is not insulated, we can add the contribution of heat, and then we'll get U2 minus U1, which we'll call as delta U, is equal to the work done on the system plus Q, and Q is the contribution of heat, that is heat added to the system. That is, the change in internal energy of a closed system is equal to the energy transfer across the system boundary in form of work and in form of heat. And due to this transfer of energy in form of heat and work, there will be change in internal energy of the system. And note that in our notation, anything that is added to the system is taken as positive. So heat added to the system and work done on the system are taken to be positive. So this is the statement of the first law of thermodynamics. Note that the first law introduces internal energy as a state property. In particular, this internal energy that we'll denote by U is an extensive property. Now, to understand this first law of thermodynamics, let's look at another example, an example that is different from the experiment of Joule. So in this experiment, let's consider a system to be a battery. This battery we'll consider in two states. State 1 would be when it is fully charged, and state 2 is when it is completely discharged. Now, there are many ways to go from state 1 to state 2. One way is that I'll short circuit this battery through a resistance. So the change in internal energy, that is U2 minus U1, is equal to the heat that is given off, and this will be the maximum amount of heat that this battery can produce between these two states, because we are not doing any work. And note that we have a negative sign over here because the heat transfer from the system to the surroundings, we are going to take it as negative. Now you can also go from state 1, that is from charged state to fully discharged state, through another process, and that process is you again consider this battery, but this time let's put a motor that drives a shaft that has a pulley, and due to rotation of the motor, this weight is raised. If we run the motor very slowly so that there are negligible friction losses, then what we can say is that this change in internal energy is equal to the work done by the system, that is this battery, and that would be the maximum work that this battery can do. Now, no matter how you discharge this battery by short circuiting through a resistor, or you discharge this battery by lifting this weight by driving a motor, no matter how you go from state 1 to state 2, this change in internal energy, U2 minus U1, is going to be the same. That is, it depends only on the states Those are the final and the initial states. Now, these are not the only two ways where you can go from state 1 to state 2. You can have a combination of these two, where you may have a resistor and a motor, or the motor is running fast and there are friction losses and there's a heat transfer from the system to the surroundings. And for all such cases, we'll have this equation, that is U2 minus U1 will be equal to the work done on the system and the heat transferred from the surroundings to the system. Now, how we go from state 1 to state 2, we could go through a series of quasi-equilibrium states, which we've called as a reversible process, or we may go through a non-equilibrium process or an irreversible process. But no matter what this process is, you can always write this equation. So the first law is applicable to any type of process, equilibrium or non-equilibrium process. However, if for a particular case, if you have a closed system that undergoes a quasi-equilibrium process, then we can write that the differential change in internal energy is equal to the differential heat dq and the differential work, that is differential heat added to the system and the differential work done on the system. And note that both of these are inexact differentials, but surprisingly, if you add up these two inexact differentials, you get an exact differential, because u is a property of the system and it's a point function. So u will depend only on the states, the final states. It does not depend upon the path. dw could be the differential work done on the system, and we've looked at examples of such work done during a quasi-equilibrium process. For example, if you have a piston cylinder arrangement in which you have a gas and the gas undergoes a volume change dV, then the work done on the system is minus p dV. Then we could write this first law as dq minus p dV, where dq is the amount of heat that is added to that gas. Now, this is the first law applied to a process. Here you have a finite process where you go from state 1 to state 2, and here you have for a differential process where you change the state infinitesimally. Now, let's consider a cycle and see how this first law can be applied to a cycle. So we can consider again system whose state can be described by pressure or volume, or it could be any two properties. If we have a homogeneous system of a pure substance. Now let's say that you go from state 1 to state 2, and you could go either through a non-equilibrium process or a quasi-equilibrium process, no matter in what way you go. And if you come back to the original state, let's say you go to state 2 from 1 and then come back to state 1, then what we know is that u is the property of the system. Therefore, the change in internal energy is going to be 0 for a cycle. And we have delta U is equal to Q plus W, and that's our first law when we apply it to a closed system. But for the cycle, this thing, delta U is equal to 0. If we start from one equilibrium state and through a series of processes, we come back to the same equilibrium state. That means we'll have 0 equals to Q plus W, and note that Q and W denote that Q is heat added to the system and W is work done on the system. and we can write this as minus W is equal to Q. What this means is that the work done by the system in a cyclic process is equal to the heat transferred to the system. And if you have this cycle that goes through a series of equilibrium states, that means you have a well-defined path, then we could also write as, for any infinitesimal transformation, we have du is equal to dq plus dw, and if we integrate over the whole cycle, this integral on the left hand side will be 0. That means we'll get minus of the cyclic integral of dw would be equal to the cyclic integral of dq. So this is a brief introduction to the first law of thermodynamics, in particular for a closed system. And in the next lecture, we'll continue our discussion and elaborate the first law of thermodynamics.